starting with the first talk of our conference, and it will be by Sören Schlichting, who is a pioneer in applying lattice methods to non-equilibrium QCD, especially to study the quark-gluon plasma, formation of the quark-gluon plasma from perturbative processes. And he has made enormous contributions. And so we also hosted a very successful program, which Rajesh mentioned. It was a almost three week program in April last year, which was very successful, and we had large number of very good participation, and many speakers. And Sören was one of our most popular speakers in that program. So we are delighted to have him back, and so we start. So we are very happy that Sören is going to give the first talk of the conference, and so over to you, Sören.
Yep. All right. Yeah. So while I put up here the sharing of my screen, first of all, let me thank you guys really for putting together this very nice program. I'm really looking forward to an exciting week, and also this very kind introduction here that you just gave. Okay. So yeah. So let's get started right away. I hope you can all hear me well and you can see my slides. Is that correct?
Yes. Yes.
Okay. Good.
Yes.
Very good. Okay, so so since this is the first talk of this meeting, I figured I would talk about. I would start by sort of giving a little bit of an overview about what we have understood about equilibration of the QGP at early times in heavy ion collisions, but then also following this sort of little bit of a theoretical discussion, also speculate a little bit on some of the phenomenological consequences that may have. So the outline of my talk is roughly as follows. So I will start with the first section, following a short introduction on microscopic and macroscopic aspects of the equilibration of the quark-gluon plasma in heavy ion collision. And then I will spend sort of the main part of my talk focusing on two particular phenomenological consequences. One of them is related to entropy production, and the other one is to the production of electromagnetic probes during the pre-equilibrium stage. Okay, so to set the stage a little bit, what are we talking about here? And so, of course, I guess one of the common goals that unites us here in this meeting is that we really want to describe the space-time dynamics of heavy ion collision. And as it turns out, well, ideally we would like to take the underlying theory of quantum chromodynamics, solve that in full generality, and use that to predict the outcome of heavy ion collision. Now, of course, that's an outstanding challenge, and we are not yet able to really do that fully from first principles from QCD. And so instead, when we talk about the dynamics of heavy ion collisions, the way that we usually picture the evolution of this system is based on essentially combining different effective descriptions of QCD, which all have their well-defined range of applicability and validity, and are somehow valid in describing this complicated reaction dynamics at different stages. So typically the collision of heavy ions, of course, starts with the colliding nuclei, which are described in terms of their partonic content, and then at high energies, the times that it takes these guys to actually interact with each other and somehow deposit the initial energy is very, very short. Now, this then leaves us with somehow a highly excited quark-gluon, a highly excited state of quarks and gluons, which initially is far from equilibrium, and so for a short time in our space-time dynamics, we really have a non-equilibrium plasma of quarks and gluon present in the system. Now, typically, from what we know from these experiments and also theoretical studies supporting this now, is that this non-equilibrium quark-gluon plasma then undergoes, first of all, it undergoes a rapid longitudinal expansion, but it also undergoes a process of equilibration, whereby sort of after a time scale of about a Fermi over C or so, we can then describe the subsequent space-time dynamics of the QGP using relativistic viscous hydrodynamics and treat the quark-gluon plasma as a near equilibrium system. Jesus. The system then continues to expand longitudinally, but later on also transversely. Thereby it cools down before eventually we hit the QCD phase boundary. the QGP ceases to exist, the energy is converted into hadrons, and this is what we ultimately measure in our detector. And so typically when we have a theoretical description of a heavy ion collision, it really consists of essentially different models describing all of these regimes. So we'd have some initial energy deposition model, there would be a description of the pre-equilibrium state, there would be a hydrodynamic state, there would be a freeze out or a particleization procedure, and then some hadronic re-interactions. Now, what I will focus about, and I guess what's also the main focus of this meeting, is somehow discussing this very early non-equilibrium stage here. And in other words, somehow trying to understand how do we take this initially highly excited states of quark-gluon matter that came out of the collision of heavy nuclei, and how does that system equilibrate and eventually lead to the applicability of relativistic viscous hydrodynamics after on the timescale of about a Fermi over C or C. And so, as it's kind of written up here, right? Addressing these kind of non-equilibrium problems in QCD is really notoriously hard, and we don't really have a fully first principles approach to that. So in the past, this kind of problem has been studied essentially coming from two different frontiers. These are on the one hand weak coupling descriptions of QCD. On the other hand, these are holographic descriptions using strongly coupled field theories, which are not QCD but are related to QCD. And so in this talk, I'll be focusing mostly on the weak coupling frontier, and then tell you a little bit about how we think about the equilibration of the QGP at weak coupling. So at weak coupling, the system shortly after the collision is typically described using QCD kinetic theory. And so in this context, there's really been a significant process in the past few years, which has actually just come from actually just taking the kinetic theory of QCD at leading order and solving it numerically on a computer and studying the basic properties that come out of these solutions. So what does that theory look like? So in QCD kinetic theory, of course, the state of the system is described by phase-space distributions of quasi-particles, of quarks and gluon, quark and gluon quasi-particles, which satisfy a Boltzmann type equation where you have the usual somehow free streaming and propagation of your particles, right? And then you have where QCD really enters the game is in the nature of these interactions that happens between the particles. And so at leading order, essentially you have to include two types of processes. The one is elastic 2-to-2 scatterings between all the constituents, and so it turns out that due to the particular nature of the way that this happens in QCD, somehow elastic scatterings with a very small momentum transfer are strongly favored. In fact, they lead to divergent matrix elements. And so to actually treat this, you have to count for in-medium effect and to account for the screening of these interactions in the medium. The other important effect that this has is that because somehow elastic scatterings with a small momentum transfer are very frequent, they happen so frequently in the medium that they can also induce radiation at the same order. Yeah? So every time essentially a hard particle gets a kick, it can radiate something, and so you have to also include these inelastic Bremsstrahlung type processes at leading order. And so typically what is done in these kind of studies to then try and start and understand the equilibration of the quark-gluon plasma is that one takes this equation, one solves this numerically as an integral differential equation. This is not exactly easy, so typically one imposes a high degree of symmetry on the system. For example, so the typical setup here will be assuming that the system is longitudinally expanding but transversely homogeneous, so that's the standard Bjorken flow setup. As I said, since the interactions here in the plasma are sort of medium dependent, so you have to account for the screening in the medium. This is solved with in-medium matrix elements for the 2-to-2 and 1-to-2 process, which are self-consistently determined. Okay, so with that, let's start and have a look at what are some of the basic, what does an equilibration process look like? Let's focus on a pure glue theory first. And I mean, most of what I'll be saying will be pure glue. There'll be an update in the later talk by Cha-Jin Du, which will show you the latest results for really full three-flavor QCD. And so, but let's first investigate what this looks like in pure glue. So, so to kind of set the stage, what I'm showing here is what I'm showing you here are kind of snapshots of the phase space distribution of the gluons in the system. So these contours are highlighting the occupied regions of the phase space distribution of gluons as a function of the longitudinal momentum and the transverse momentum over here. So typically the state that is produced in the collision is highly anisotropic. Okay, so typically in the local rest frame, the particles will carry a much smaller longitudinal momentum as compared to the transverse momentum, which is the transverse momentum is mid rapidity is large. Okay, and so initially the plasma will essentially have two features. It will be in a highly anisotropic state, and it will have rather high energy degrees of freedom present here with typical energies on the order of, well, we would call this the saturation scale, but you can say a couple of GeV or so maybe. Okay, so there's this highly anisotropic and potentially also dense state at initial times. And so the question is now, okay, how does the system go from there towards approaching a state of kinetic equilibrium? Okay, and so, well, you could think that, for instance, well, an efficient way would be to just try and isotropize the momentum distributions. However, it turns out that these elastic processes, because they favor a small momentum transfer, they're actually very inefficient in somehow just isotropizing the system. And so instead, what will actually happen is that these hard particles present in the system, they will, triggered by these elastic interactions that they undergo, they will radiate softer and softer gluons. Okay, and so at some later time, if you look at the distribution, then you will see that you will have sort of a densely populated soft, but here you have this kind of tail of collinear radiation of hard particles, which still carry most of the energy, but there's sort of a soft component, soft bath building up. And so eventually what happens is that this soft bath, the particles in the soft bath become sort of more and more abundant, and you end up with a situation where essentially you have a few hard particles left in the system, which lose their energy towards the soft bath, very much like a jet losing energy towards a thermal medium. And then sort of in the final stages of equilibration, what happens microscopically is that these hard particles undergo multiple of these successive branchings, become softer and softer, feed all their energy to the thermal bath, which where of course at these low scales elastic processes are much more efficient, and they tend to restore the isotropy of the system. And so this is, I mean, what I'm depicting you here is nothing else than what's the famous bottom-up thermalization scenario, which was kind of in its structures discussed almost 20 years ago. Okay, so just to show you this, I mean, you may say, okay, well, this all sounds very natural, but I mean, it's not necessarily that things happen exactly like this, right? So this is the result for QCD kinetic theory. Now you can also study different models of equilibration, and just to give you this as a comparison, because I'll be frequently comparing different theories. Here's what happens in the relaxation time approximation to the Boltzmann equation. So in the previous example, we had all these detailed collision integrals of QCD. Okay, now instead, what you may also study this in the relaxation time approximation, where you say, well, I basically just assume that everything that's out of equilibrium will relax away, and I will just build a system with the same amount of conserved charges, which defines the equilibrium system. And so there you can see, well, if you were to actually study that, the evolution of the phase space density would be completely different, and you wouldn't see any of these kind of patterns that really characterize QCD. Okay, so this is roughly speaking the microscopic picture that we have. Now, what about the macroscopic properties of the system? And this is actually very interesting, because what at the end of the equilibrated stage we want to do is we want to match our pre-equilibrium description to hydrodynamics, and hydrodynamics by definition only cares about the macroscopic properties of the system. And so what is interesting is if you now compare a number of these very different microscopic theories, then it turns out that despite the fact that there are very clear differences at the microscopic level, the macroscopic feature of these systems actually all behave in a very, very similar way if you compare them in a meaningful fashion. So one of the things I showed you here is that the system initially is highly anisotropic. So to go towards a description in hydrodynamics, one of the things that you want to understand is, for instance, how how the anisotropy of the system evolves. And this you can quantify as a ratio in terms of the ratio of the longitudinal to the pressure to the energy density, or alternatively longitudinal pressure to transverse pressure. And so the time evolution of this quantity is shown here for different underlying microscopic models. So one of them is pure glue QCD. There's also the relaxation time approximations. These are the two I discussed previously. There's also strong coupling calculation here. And finally, there's the viscous hydrodynamic asymptotic shown. So what you can see is that despite the fact that the microscopic evolution is very different, they all kind of show a very similar pattern. We're starting from this highly anisotropic state early on. The pressure actually relatively quickly builds up. So this is a logarithmic scale here. And then eventually approaches the viscous hydrodynamic behavior. Now, what is interesting about this is, on the one hand, you may ask, what is the time scale for this approach to viscous hydrodynamics? And so here I've said the theories are similar when you compare them in a meaningful fashion. And so to compare them in a meaningful fashion, what I've actually done is I've compared them in terms of by plotting, so to say, the evolution time in units of the kinetic equilibrium relaxation time, which is determined by the shear viscosity to entropy density ratio. So that's a measure for the coupling strength of the system, and the effective temperature, which is just the temperature of the thermal system, essentially. And so if you normalize it like that, then essentially what you find is that this approach to hydrodynamics, or the system, starts to become describable by viscous hydrodynamics on a time scale of essentially 1 unit of this equilibrium relaxation time. Now, the other thing that is interesting about this, and this also has emerged in a number of contexts, is that if you look at under what conditions does viscous hydrodynamics start to describe this evolution, then this actually happens when the pressure anisotropy is kind of order 1, right? So the longitudinal pressure is still much smaller than the transverse pressure at this stage. So in equilibrium, they would both be at something like 0.3. And so this phenomenon of hydrodynamization actually occurs very much before the system really truly becomes isotropic. So hydrodynamization, or applicability of hydrodynamics, by no means implies kinetic thermalization, but happens much earlier than that. And indeed, if you now somehow turn this equilibrium, turn this estimate, hydrodynamization happens on the time scale of 1 equilibrium relaxation time into a realistic time scale for heavy ion collisions, then you find for sort of typical parameters in a heavy ion collision, so eta over S is 2/4 pi, and say entropy density of lead collisions, then you find that hydrodynamics becomes ecliptical on the time scale of 1 Fermi over C also. Okay, now there's one more. So now this isn't really the full story yet with regards to the macroscopic properties, but there's something else that is very interesting about this. And this is also something that I'm sure we will hear a lot more about this week, which is related to what in the field we now call these hydrodynamic or non-equilibrium attractors. Namely, if you consider in particular weakly coupled theories. For strongly coupled theories, there's sort of a discussion whether or not this applies or not, you may ask yourself, okay, now you have shown me here what in red, say for instance, you have shown me one particular evolution of the pressure to energy density ratio, but how sensitively, for instance, does this depend on the initial condition? Okay, and the answer is that in these weakly coupled theories, actually, this is rather insensitive to the initial condition. And in fact, there's some kind of, at the macroscopic level, there's some kind of effective memory loss occurring at very, very early times, actually before the system approaches hydrodynamics. And so you can see this here kind of in terms of these gray curves, where if you, instead of, starting your system on this red line, you varied the initial anisotropy a little bit, or you started a little bit later. Actually, what this will do is they will always relax towards these non-equilibrium attractor curves, and this will happen on a timescale which is actually given before even the onset of hydrodynamics. And that is sort of interesting, okay? Because really what that means is that to a certain extent, one can think of these attractors curves as providing you with some kind of effective constitutive equation for a far from equilibrium system, where well, in equilibrium would have some kind of equation of state. So your pressure over energy density would be 1/3. Out of equilibrium, there would be viscous correction. So you would have something like that. But now very far from equilibrium, essentially, this is now extended to even earlier times by having some attractor function, which depends on both the energy content of your system, or which essentially depends on the time in units of the equilibrium relaxation time. Now, these non-equilibrium attractors, they are different from, say, our ordinary theory of hydrodynamics, in the sense that they are actually, as you can see here, they are different for different microscopic theories, right? So even though all these theories have been normalized such that they have the same hydrodynamic behavior at late times, what you see is that the corresponding attractor curves are actually different. Nevertheless, there's somehow a universality of the attractors in terms of early and late times. So at late times, of course, all theories eventually go to their hydrodynamic long time, long wavelength limits. Whereas at early times, the system kind of looks macroscopically free streaming. So it's simply not possible to maintain a large longitudinal pressure at very early times. Okay, so this is the picture that happens for Birkenflow. Now you may say, okay, this is all fine if we kind of understand the average behavior of, say, the energy momentum tensor, but really we want to go ahead and describe heavy ion collisions. Okay, and so, I mean, one of the prominent features of heavy ion collisions is that, of course, heavy ion collisions, they have very complicated spatial profiles in the transverse plane, right? And that's what eventually leads to development of flow, and that's what we measure in the experiment. So really what we should be able to provide from the pre-equilibrium perspective is we should be able to kind of map all these profiles out and then construct some initial conditions for hydrodynamics starting from there. And so, so now while for a system undergoing Bjorken flow, this is, I mean, these kind of things nicely show how, say, the pressure relaxes. The question is how to extend this to sort of systems with more detailed spatial profiles. And so the idea that we developed in that context was actually the fact that, okay, if we have such an explicit memory loss at very early times, we don't really have to go here and describe the phase-space distribution of gluons in each step, but in principle, one can kind of build a macroscopic description of the pre-equilibrium stage starting from the very beginning, and essentially just construct just describe even the pre-equilibrium evolution in terms of macroscopic quantities. And so, so if you think about this problem for a little bit more, then if you actually want to do this evolution over a short period of time only, then in each point that you look at, somehow only a very small number of points can contribute, because simply the points that can contribute are limited due to causality. Okay, and so so the idea was then that in each of these kind of causal patches, you can essentially go ahead and say, well, okay, here fluctuations around sort of the local background are not so large. Okay, so I can kind of describe this as a homogeneous local background plus small fluctuations on top of that, and I can then essentially study the evolution of macroscopic quantities. In the pre-equilibrium stage by essentially taking in each of these cells, each of these causal patches, taking the non-equilibrium evolution of some local average and homogeneous background and study small fluctuations of that using essentially linear response theory, so propagating them with some kind of Green's functions. And so we set up a framework like that with this, which now comes under the name of compost, and really goes really performs such a event-by-event pre-equilibrium dynamics. Now, this is interesting for at least two reasons, okay? Because one of them from the theoretical side is that, of course, it allows you to study equilibration beyond this simplifying assumption of having a boost invariant Bjorken flow and in homogeneous transverse systems. So at least you can study somehow linearized deviation from that, which are then given in terms of these Green's functions. And so these Green's functions are, of course, again, things that are calculated within the underlying microscopic theory. Now we have calculated these using different microscopic theories. So here again, I show you some plots of these Green's functions. So for instance, what this left panel shows here is how, if you have an initial energy density spike, how that gets smeared out and pushed in different theories. So the full lines here are calculations using, again, the relaxation time approximation. The dashed lines are full QCD kinetic theory, and what you can see again is that this is very largely insensitive to the underlying microscopic dynamics. The other thing that this allows you to do is that, of course, if you can now really describe the pre-equilibrium dynamics in full glory, you can embed this into a full hydrodynamic description of the entire event, and you can study now what is actually the impact of this pre-equilibrium stage on typical observables in a heavy ion collision. And so this is shown in the lower panel over here, where we actually did this. So the red points here really correspond to a full this macroscopic kinetic description. Then you can do just sort of a scaling of the energy density. You can also do free streaming, okay? And you do see, well, okay, there's sort of a smallish effect on the observables depending on what you do within the pre-equilibrium stage. However, this is really not that large. So even if you do nothing, you ignore pre-flow completely, say for instance, then you would still end up with rather similar results, say for instance for V2 or also the mean PT that you have here. And so generally this is of course to be expected, right? Because you're dealing with this sort of short one Fermi stage at the very beginning of the collision. And so this is both good news and bad news, right? Because on the one hand, you can say, well, okay, the fact that this pre-equilibrium stage is perhaps not so important for observable is nice because it allows you for controlled extraction of near equilibrium and transport properties of the QGP based on hydrodynamic simulations. However, this is also bad news from the point of view that it gets hard to get access to non-equilibrium dynamics from experiments. Okay. So with that, I would. So this was kind of my brief overview on equilibration. So with that, I would now like to come to some cases where we are actually, or where we think we can actually access some of the pre-equilibrium behavior. And so the first topic that I would like to address is that of entropy production. So I said that generally we're rather insensitive to the behavior of these early stages. However, there's of course an important exception, and that is with regards to entropy production in heavy ion collisions. Now, why could this be the case? Well, the first thing is that, of course, entropy production only occurs when the system is sort of significantly out of equilibrium, and in a heavy ion collision, this is primarily the case at very, very early times. And so for that reason, you should expect that entropy production is somewhere dominated by the early stages. Now, the other thing is that this is also something that we can actually access in experiments, because basically what happens is that the entropy that is contained inside our QGP fluid at the time of the freeze out is essentially converted into charged particles. And so this is something that actually is the simplest thing to measure in experiment, right? I mean, if you just measure the charged particle multiplicities, you basically directly probe how much entropy was produced. And so what I'd like to show you now briefly is that how, with the understanding that we have now in terms of this non-equilibrium stage, we can really construct a map between how the initial energy density is mapped to the entropy at hydrodynamics, which then, due to the nearly isoentropic expansion of the QGP, equals the entropy at freeze out, and that becomes then measurable in terms of the charged particle multiplicity. Okay, so how do we go about that? So to study entropy production, of course, we start from a highly non-equilibrium state, and so that non-equilibrium state is actually better characterized in terms of its energy density, and so I'd prefer to only use entropy or the notion of entropy once the system is close to equilibrium. And so, as in the previous part, generally the way we'll do this is we'll kind of think of this local process of equilibration, so study sort of local homogeneous patches of the QGP, where then the energy momentum tensor is simply of this averaged diagonal form. So we have energy density, transverse and longitudinal pressures, and you can simply write down the conservation equations for this system, where you will see that, okay, starting from an initial energy density that's there, so that's what was deposited in the collision. To predict the evolution, we'll need two types of things. On the one hand, the energy density will drop due to the longitudinal expansion, but then there's also work done against this longitudinal expansion, which makes this relation sensitive to the longitudinal pressure. And so to actually just integrate this conservation law and somehow, so to say, study the evolution of the energy density until the system is equilibrated, we need one additional relation, which is the pressure as a function of energy and time. Now, this now brings me to why these insights are useful. So what do we know about these kind of relations? Well, of course, in equilibrium, there would be an equation of state, right? Near equilibrium, one could do a hydrodynamic gradient expansion. So this is written here for conformal system. Okay, so pressure over energy would be a third in equilibrium. To first order ingredients, there would be a viscous correction. Now, in principle, for far from equilibrium system, there is no analogous relation to that. Okay, in principle, in a non-equilibrium system, your pressure over energy density can be anything, right? But now, as I've shown you before, it seems that in this, at least in the setup of Bjorken flow hydrodynamics, we have these non-equilibrium attractors, which actually do provide us with something like an effective constitutive equation, where now the pressure over energy density is some function of essentially of this variable that I call W tilde, so essentially essentially a ratio of the expansion rate compared to the equilibrium relaxation time. Okay, and so if you actually then combine this, so you take the conservation law and you take the effective constitutive equation, then you can plug that back in here, sort of do a rearrangement of variables, and that really allows you to actually characterize the evolution of the energy density. So you can basically just integrate the conservation law. You see you'll be sensitive to pressure over energy density. There's some other term that comes from a change of variables. And yeah, so knowing the state of the system at some early time, you can then basically predict how the energy at the very early stages is converted to the final thermal energy density when hydrodynamics in the system is applicable. Now, rather than showing you this map kind of starting from zero, integrating this equation from zero, I would actually like to integrate it the other way. Okay, so I'd like to sort of integrate it backwards from infinity. Okay, and so to say, normalize the energy density to its final value. And so this is what I will call the energy attractor function. Which is then shown over here. So generally this looks like this. Okay, so if I normalize to the end, then eventually this will approach unity. So this at the end, the system will essentially exhibit its equilibrium Bjorken flow, and the energy density will become constant if I normalize it to the final time. Whereas at early times there will be this free streaming behavior, which in this case corresponds to a single power. Okay, so now, as we had seen, is that different theories somehow give us different pressure evolutions during the pre-equilibrium stage, right? But these different pressure evolutions, of course, now affect the efficiency with which the initial energy density is converted to the entropy or to the energy density at the time that hydrodynamics is applicable, right? And so if you now put together all these different curves, then essentially what you will see is if you kind of all normalize them to reproduce your correct final state energy density, then you'll need different amounts of energy density at the beginning to reproduce that same amount of energy. And this you can characterize by essentially just one constant, which is the amplitude in terms of in front of this free streaming behavior. So irrespective of the underlying microscopic theory, at early times, the system essentially has this almost pressureless expansion. So this energy attractor curve will be simple power law times a constant. The constant varies from theory to theory, whereas at late times, they all go to the same. Microscopic, to the same viscous hydrodynamic behavior, where pressure is 1/3 plus viscous correction. Okay, and so what's interesting actually about this within all of the theories that have been studied, right? This conversion efficiency, which is here characterized by this constant C infinity, actually varies very, very mildly between the different theories. So in QCD kinetics, you have something like 0.87. In strong coupling, you have 0.16. Okay, 1.06, right? And so it's kind of a 10 to 15% spread. Okay, so so this allows us to somehow relate the initial energy density to the energy density at equilibrium. Now, how do I make a formula for entropy production out of this? Well, this is very simple, right? Because once the system is close to equilibrium here, right, I can, of course, simply use thermodynamic relations to now calculate the entropy per unit rapidity of the system once it's close to equilibrium, right? And so basically, you just take this energy density map, and you can then calculate the entropy production, which depends on the initial energy density, some non-equilibrium transport parameters, and the equation of state. And since following the applicability of hydrodynamics, the system remains close to equilibrium. The hydrodynamic expansion is nearly isentropic. This entropy that was there at the beginning of the hydrodynamic stage is then basically converted into charged particles at the end when the system undergoes hadronization. And so with this, you can then really go and predict the charged particle multiplicity as the entropy per unit rapidity when hydrodynamic applies times the transverse area at that stage times the number of charged particles per unit entropy in a hadron gas. And so collecting this together, right? So based on this macroscopic theory of hydroextractors, right? You can really then have a one-to-one correspondence between something that was there at the very beginning, the pre-equilibrium stage, and what is really outcome in the experiment. Okay, and so this is kind of the final formula that we came up with. So now let's walk you through this. So if I look at what determines somehow how many particles are produced in the event, okay. So then there are different kind of factors appearing. So the first one is the entropy. This is converting our entropy to charged particles. So this is just charged particles per unit entropy in a hadron gas, and that's roughly 7. Okay. You need to also match energy density to temperatures. For that requires the equation of state in the high temperature phase. And so this we parameterize in terms of some effective number of degrees of freedom. That's in principle something that's known from lattice QCD. Now there's also there's other things that you know. You need to know the size of your system, of course. Okay, this we also know at the very beginning, right? That's just essentially given by the overlap area of nuclei. Okay, that's fine, right? But then the non-equilibrium and transport properties, they're also I mean, the final amount of charged particle production is extremely sensitive to those, right? And so these are characterized on the one hand in terms of this constant, which tells us how efficient are different theories in converting the initial state energy density to the energy density in equilibrium. And so that's, as I said, that's something like roughly 1, okay, with 15% error bars, and so surprisingly well constrained actually from comparing these other things. The other thing that is that shows up here is the shear viscosity to entropy density ratio, and that. Of course, that also enters here because that essentially sets the time scale for equilibration, right? I've told you, okay, equilibration happens on a time scale of 1 equilibrium relaxation time. That's determined by the shear viscosity, right? And so if you equilibrate earlier, you will do more work against the longitudinal expansion. And so that's why this constant enters here. And so note that this is actually entering as a kind of a pure power. So in principle, this is very, very sensitive to the eta over S in the high temperature phase, okay? So that's really during equilibration, and that's perhaps something that we don't know that well. And then finally, there's of course the initial energy density, okay? And so, so if we look at that and we were to sort of go about, we were to go about actually trying and calculate that, again, there would be significant uncertainties associated with that. So at least so let's put it like that. At least there are two things in this formula that we perhaps don't know that well. Okay, but nevertheless, I think this is very interesting, right? And so to kind of illustrate this a little bit more, let me show you this plot here, where essentially what I've done is I've kind of reverted the formula. So taking now the measured values of the charged particle multiplicity, and from that re-extracted the initial energy per unit rapidity. Okay. So this shows this kind of extractions at in the left, so in the energy per unit rapidity as a function of collision centrality at RHIC and at the LHC. Okay, and of course you can also compare that. So the gray bands here correspond to our extractions, where actually you get such large bands by simply varying the shear viscosity within 1 to 3 times 1/4 pi, and varying this constant C infinity. So this is the pre-equilibrium and transfer properties of the QGP. And so what you can see is, first of all, if you compare this to the experimentally measured energy per unit rapidity, you see that, okay, the initial one is always higher, and that is clear because that is due to the work done by the longitudinal expansion. Now, what is really striking, though, is somehow the actual size of that bands that you get with varying the parameters within sort of conceivable margins. Okay, so these bands almost span like factors of 2. Okay, but that really tells you also, you know, what power that actually has to really take into account the pre-equilibrium conditions, and perhaps try and go to really do as good as you can computation of the initial state, right? Because if you were to be able to somehow calculate the actual initial state energy within 50 or 30% uncertainty, this would correspond to something like here, right? You would see there would be a relatively strong constraint on somehow what can actually happen in the process of entropy production. So in other words, what can be your values of eta over S. And so I think this really bears a lot of potential to somehow have a combined constraint on both properties of the very initial state, which reflect properties of essentially nuclear gluon distributions, and QGP transport properties. And so I think that's a very interesting link that's now starting to show up between somehow the physics that we look at in heavy ion collisions and the small x physics that we look at, for instance, or that will be looked at the future electron ion collider.
Sören,
I have
4
something
minutes,
like 5 more minutes. Yep. Okay.
Yeah, 4 minutes actually.
4 minutes precise. Yeah, that should be fine. Okay.
Yeah.
Okay, very good. Because so this last point is so this last point is going to be rather brief. So I only have like 3 slides. Okay, so please feel free to shut me down. Okay. So so the point here was that, okay, we have found something that is sensitive, which is entropy production, but okay, to actually fully deal with this requires a lot of work, and it's somehow also somewhat indirect, let's put it. So what about other things? So another thing that could come into your mind to actually probe the pre-equilibrium stage would be to study the emission of electromagnetic probes. And so we have recently started to look into this with people from Saclay. Actually, it was driven by experimental efforts. And so the idea here, of course, is very simple, and it's also not entirely new, right? So Mike and my collaborators have looked at this a long time, but the basic idea is that electromagnetic probes are produced throughout the entire lifetime of the QGP, and they escape the plasma without re-interaction, right? So if there's any particular feature you can identify about electromagnetic probes from the pre-equilibrium stage, well, maybe you can be lucky and you can measure it. Okay, so we decided to look at Di-lepton production, where if you look at the rate at leading order, there's essentially, so this is the leading order process, quark-anti-quark pair annihilation into Di-leptons. There's essentially some QED part, and then what you have to worry about is the current correlation function inside the medium. And so if you look at this in the limit where the invariant mass of the Di-lepton pair is much larger than the temperature, then essentially this is just given by essentially this whole production yield is just proportional to the Bose-Einstein distribution. Okay, so now, of course, the next thing you have to ask yourself is what is actually different. So this would be the equilibrium production rate. What is actually different out of equilibrium? Okay, so the first thing that is really the most important thing is that the non-equilibrium PGT is, of course, the state at the very beginning. Okay, and at that stage, the plasma is hottest. Okay. So in a sense, the kind of effective temperature that you have in your system will be the largest, okay? And for that reason, you may expect to actually produce very highly energetic di-lepton pairs, which are very, very hard to produce later on, okay? Now, of course, this estimate in this form doesn't no longer hold, and so you actually have to modify this because also the system is highly anisotropic and can actually also be not in chemical equilibrium. So there can be fewer quarks present at this. But so the basic idea is that, okay, if you use the fact that the typical energy density is highest at the beginning, you should move as high as you can on the energy scale and explore high invariant mass di-leptons as a probe of the QGP. So we looked at this. So we started to look at this a little bit, and for again, we wanted to exploit this insights on the attractors, right? And so essentially, we came up with sort of a simple procedure where we basically said, okay, let's just do this thing where we parameterize the quark and the gluon distributions by taking into account essentially an anisotropy and an effective temperature and potentially also a suppression of the quarks at early times. And then we simply match these parameters psi, which is the anisotropy parameter, and the effective temperature to these attractor curves. So the anisotropy parameter, of course, can be matched to the longitudinal pressure to energy density, and the effective temperature can be matched to the evolution of the energy density for these non-equilibrium attractors. So basically, the input to this are these kind of pressure over energy density curves and the evolution of the energy density. Now, so far we didn't account for this for quark suppression, but this can be easily included if you somehow consider the energies of the additional species. Okay, so last result. Okay, so now you can ask yourself how much. So what is the role of sort of the late stage hydrodynamic production of these di-leptons compared to the pre-equilibrium production? And so for this, essentially, I've distinguished them by whether we are in the hydrodynamic regime or whether we're in the pre-equilibrium regime, based on this usual ratio of time in units of the equilibrium relaxation. And so what you find is that, well, again, depending on the value of your shear viscosity, here it's very small, here it's 2/4 pi, right? You can actually find a large invariant mass window where really this pre-equilibrium stage dominates. Now, if you actually compare the actual production yields at different shear viscosities, somehow the sensitivity is a little bit reduced, because of course you have to add up the two contribution, right? But I mean, I think for conceivable values of eta over S, there can really be a large pre-equilibrium contribution sitting out here in the high invariant mass range. Now, of course, there's a problem with that here, so you can say, well, why don't you keep going indefinitely? Of course, at some point from higher scales, there's other effects that come in here, in particular Drell-Yan, and there are also contributions from jets. So we're working on estimating the Drell-Yan at the moment. But I think this is nevertheless a very, very interesting avenue of kind of pursuing these electromagnetic probes further. In particular, also, if you think about chemical equilibration, and so that was a point that was nicely given in this paper, because for the di-lepton process, I told you this is quark-anti-quark annihilation, right? So naturally, you need quarks and anti-quarks present in your system, so the di-lepton production goes as the square of the distribution of quarks, right? Whereas for a photon, you basically have quark-gluon scattering, and so photon production goes as the first order of the process.
Sören, sorry to interrupt, but we need to really wind up very quickly.
Okay, good.
So that we have time for questions.
Okay, so with that, I'll just flash my conclusions here. So I think there's been a lot of progress in understanding these things. We have tools in place to do this, and we have different ways to probe. I think ideas coming up to how to probe these pre-equilibrium stages, and I think that's the main message I wanted to convey here. Thanks.
Thank you, Sören, for this great talk and very interesting talk. And now it is time for taking questions. It looks like most people would like to ask questions in person. So please turn on your video, unmute yourself and ask.
I didn't hear anything so far.
Yeah, I think it's there will be questions for sure. So,
it's in comment section.
So I see questions by Mike in the chat. I mean, if you want me, I can start to address them.
Yes, so you can maybe want us to read out the questions first, better like that. So I can read it out. So Mike's questions are, Firstly, is there any problem in matching kinetic theory to IP plasma caused by the fact that pressures in IP plasma can be negative, whereas kinetic theory is always positive? And can the pressure be also negative in compost? That's the first question.
Yep. Okay. So so in principle, okay. So why is the so let me ask the one. So why is the pressure negative in IP plasma? So the pressure is negative in IP plasma because essentially you haven't waited for the formation time of for quasi-particles to form, right? So and if you match this to, I mean, if you match this to a kinetic theory, in kinetic theory, evidently the pressure is positive, and so. So that doesn't necessarily make sense. So you should wait until that has happened and then match. That's what I would say. So in actually the current version of compost, it cannot be negative. And in principle, what is done there is actually that the longitudinal pressure is directly put onto that attractor curve. So even if this was your pressure to start with, you would actually put that pressure here. Now the point is essentially that this is a kind of a fluctuation that very quickly will be forgotten and should be and we didn't propagate it explicitly. Now in the future, what we want to do is we want to actually include these type of fluctuations of the energy momentum tensor as well and propagate them alongside also, and with that it would be allowed. Second question is, are plasma instability considered in this process? And the answer is no. So this essentially comes to the discussion of how one deals with screening inside the medium. So all these studies are performed under the assumption of isotropic screening here.
Also another comment by Mike. It is a comment for slide 21. It is an so there's you must go to your slide 21, please, if possible. Yeah. Yep. There is a paper, or maybe Mike can make a comment himself. Yeah.
Yeah, I'm just pointing to an earlier paper because he pointed out this Gail Jean paper about di-leptons and the sensitivity to the early time.
This year, you mean? Yeah.
Fugacities, right? So I just wanted to point out that people were thinking about this in 1994.
Okay, good. Okay.
Sorry to be a little Russian.
Yeah, sorry. I was 7 then.
Okay, Sayantan has a question. Is there an understanding why both strong coupling theories and kinetic theories have same hydrodynamic attractor? But I guess not, right? That's what you were saying.
Well,
they don't have the same hydrodynamic attractor, no?
So yeah, so the question is, what do you mean by the same, right? So clearly so let's go to this slide here. So clearly these things are clearly these are different. Okay, so I mean, first of all, they are different curves, and the only place where they are really identical is the regime where the hydrodynamic gradient expansion is applicable, and there by definition all macroscopic all theories which have the same macroscopic behavior have to be the same. Now the point is that at least for weakly coupled theories, so usually you would expect, okay, when do you use memory loss? Well, you use memory loss at the time scale of equilibration. But for weakly coupled theories in this strongly expanding setup, it turns out that the expansion also sets a time scale which leads you to kind of drop your pressure and relax it back here. So for the weakly coupled theories, you can, I mean, this has been shown that they always relax to these kind of attractor lines already on early time scales. Now you can see for the strong coupling calculation, this is, I think, to some extent under debate. Well, I mean, there's actually people who would say the opposite, that for strongly coupled theories here, really you only relax at very late times. And you can see this here. So the green curve, this is a relatively late time, right? And these are still going here, and here the pressure can be anywhere. The thing is, I don't know whether these initializations, which give you crazy pressure behavior at early times, here are in any means physical in these strongly coupled theories. Okay.
Okay, so Shamapan has some questions. It is I think the first question is whether the isotropization is always happening in the non-equilibrium phase, and the second question is, does inelastic collision help in isotropization? Okay,
so essentially this is also, so the answer to this is also on this plot. So the first question at least is also on this plot. So I mean, the question is, what do you call the non-equilibrium phase, really, right? So, I mean, this is, to a certain extent, the system is always out of equilibrium, right? The question is whether, it's describable by hydrodynamics or not, right? And so typically it starts to become this, as I said, describable by hydrodynamics on the time scale of 1 equilibrium relaxation time. And there the system is actually still fairly anisotropic, right? So the transverse pressure is, I guess, twice as large as the longitudinal pressure, right? So a lot of the pressure relaxation at the end seems to be actually captured by viscous hydrodynamics. Now, the second part of the question was about elastic and inelastic processes, right? So let me just reiterate that. So essentially, so the inelastic processes, they help, so to say, that they make your particles softer, okay? But typically, the transverse momentum generated in the splitting is parametrically small. It's treated as 0, actually. So the actual isotropization happens at low scale, mainly through elastic processes, actually. So inelastic processes make your things softer, and then they can more easily isotropize.
Tony has a question. What is eta by S in YM kinetic? Is that not time dependent?
No, it's actually a constant. So it's a constant that only depends on the coupling strength. And since the coupling strength is fixed here, that's actually a time independent constant. The exact value, I mean, so typically we run, typically we run these simulations at Toft couplings between 5 and 20, and then eta over S is still somewhat larger than the phenomenological values you would use, but yeah. The actual value only depends on the Toft coupling in Young-Mills kinetic theory.
Okay, so I think the question about, I don't know, but Tony's question probably is that isn't there some temperature dependence of eta by S in YM kinetic?
No. This was precisely the point. It's only a function of the Toft coupling.
Okay. So
I mean, at leading order,
feel
right?
free to also ask questions,
right?
and yeah.
Who asked question? Sorry.
I see. No, I'm saying just to everybody now, people can just also ask questions in person. I mean by turning on the video and unmuting. Okay, Sayantan has another question. Sorry, Tribhuvan has first question. If the quarks and gluons are strongly interacting, why are we using weak coupled theories like Boltzmann RTA to describe equilibration?
Well, okay, so this question has a number of facets. Okay, so first of all, we should clarify about what are the conditions that we talk about here, right? So the conditions that we talk about here are somehow this sort of early stage. Okay, and so at this early stage, we have temperatures in excess of, say, sometimes like 4 times the transition temperature. Okay, and so at least for static quantities, for what it's worth, right? We know that this is a regime where somehow Brisam perturbative descriptions can work. Okay. Now, that being said, as I mentioned on this slide here, right? Okay, I mean, in principle, we want to study full QCD without doing any kind of approximation and just go. Okay, but to some extent, we have to live with the theories that we can use to study it, right? So what I used here was leading order perturbative QCD. Okay, I contrasted this with a few other models, right? But yeah, I mean, we have to live. I mean, to a certain extent, we have to live with the theoretic descriptions that are at our disposals. And the thing is, there are not so many out there, right? I mean, if you know how to do this in full QCD, please go ahead and do it. I'd be the happiest person in the world to see the result.
Well, I mean, there's a stronger argument, right, that early times, because of a large temperature scale, truncating at leading order might be the thing that kills you. But there's some hope that perturbation theory will work to describe the early time dynamics.
Yeah, sure. And I mean, so sorry if I may. So to bring you in, I mean, what we do, of course, in these studies also, right, is we study this, at least within our weak coupling description, we study this at various coupling strengths, right? We look at whether, things change as a function of coupling strength significantly, and we do this kind of extrapolation towards realistic coupling strengths in a way that actually things essentially turn out to not depend on the coupling strengths anymore. Yeah. Sorry, I interrupted you a little bit.
So Sayantan has a question. Okay, so Sayantan has a question. Maybe this should be the final question because now we have to start. We have to go to the rest of the session. So Sayantan's question is: when you are matching initial energy density to final multiplicity in your way, are you assuming actually isentropic expansion? And the second part of the question is the bulk viscosity not relevant for this matching? Why only eta by S?
So I'm assuming isentropic expansions, and I mean, you can look at this, what happens in the hydrodynamic phase also, and I mean, entropy production in the hydrodynamic phase really is a few % effect. Okay, so you make a few % mistake, but it's really not a dramatic effect. Actually, I think I have a plot of this even in the backup. The second question is the bulk viscosity not relevant here? I'm not sure. Relevant to what?
Relevant for the matching, I think. And his question was about isentropic, not actually isentropic.
Yeah, this is a good question, and this is something that we, I mean, hasn't really been, I mean, so to say, with the tools that we have at present, hasn't really fully been investigated to the best of my knowledge, because one of the things that all these theories that I showed you here have in common is that they're conformal, actually. Okay, so there is no bulk viscosity in these theories. Now, again, we are dealing here with the, with the very high temperature end of things, right? Where presumably bulk viscosity is very, very small. Okay, so for that reason, one may hope that this is, I mean, at least for some other center of the collision and the hotspots, this is presumably fine. Now, there have been some voices raised that if you actually use these kind of practical tools that we're putting together, whether at the edges of the collision, there are some artificial effects due to missing, or due to essentially conformal description, and this is something that I think has to be investigated further. Yeah.
Okay, thanks, Sören, for this beautiful talk again. And
yeah, thanks very much.